Earth and the Sun, together with all these other planets, we already know that other planets affect how our orbits is changing over much longer time scale. So it's on the order of what they call the Milankovitch, right, time scale. Those things will affect how our orbit tilt from 23.5 to about 24, you know. And then how the orbit precess, like a spinning tops. Sometimes, like, you know, 11,000 years ago, now we basically have the winter. We are furthest away, we are nearest to the sun, right? But 11,000 years ago, our nearest distance to the sun is during summer, right? So those precession, and then the changing of the shapes of the orbits, which is either more elliptical, which is almost 4% to perfect sphere, a circle, which is a circle, right? That's 4% kind of change, and that is over 100,000 year time scale and 400,000 year time scale. Those regularity come from basically Jupiter, Saturn, and all this other stuff, including even inner planets. Like, for example, Venus is causing our stuff to modulate about 1.6 years. Okay, so we're talking about things that changes over this whole continuous spectrum. This is why to study this class of problem, you really have to be very broad-minded and broad disciplined, because it takes that sort of different solutions to try to put together the more comprehensive picture. So that has always been my goal from day zero. So it's doubly disappointing when you come into a new area and realizing that these people only want to study carbon dioxide, which is really strange. So let me start. So you really need to know how the orbit changes over time. And then not only that, I have known this problem for a long time, that on every few years, first of all, season, 1 year, right, 365 point some days, and then plus that you have this, you know, what you call the odd even leap years and all that business. That's why keeping calendar is a very difficult problem. You need accuracy. 1 year, and then you realize that all the short time scale, interannual time scale, so every 2 years, every 3 years, if you like El Nino, we need to know, is El Nino truly something that's changing internally to the system, or there's something not so apparent from the outside? That's the question I want to answer. And it turns out that our orbits have enough of a signal and regularity in this multi-annual timescale to the issues of decades, to the issues of 60-year, multi-decades, to the issues of centennial, to the issue of bicentennial. Those are specific time because they are related to how the orbit perturbs our relative changes to the thing. Plus the moon, don't forget, the moon. Because the way the sun see our system is actually not the earth only, it see both. Because the sun have a tidal effect on us and the moon have a tidal effect on us. So these things are inseparable. This is the class of problem that no wonder you cannot trust the climate model, right? Only for weather prediction you can do that. But if you want to understand tide, I'm sorry, you have to have moon, right? Not only that, you have to have sun. Sun have a solar tide on us also. Especially if we really want to understand atmospheric phenomenon in the ionosphere. Those things are all really relevant. On top of that, the sun itself is a giant hot gas ball, right? Deep inside, you have this nuclear generating core that is on the order of inner 20%, 10 to 20%, so of the inner core. It's basically so dense and so high temperature that you have hydrogen fusing and forming deuterium, and then two deuterium form this thing to make helium. So out of it, basically where helium comes from. It's from internal of the core. Then you have an outer region where mostly a reaction to this. So you form a region, there's another 30% of this thing, so 40% or so. It's called a radiative transport zone, where all the energy, because it's so dense, the photon, by the way, doesn't get seen from the outside. It takes bouncing around because it's so dense that it bounces around at least 100,000 years. By the way, the time scale is so strange because it's exactly coincide with the Milankovitch time scale of 100,000 years. And then another outer region, which is the way in which the sun cools itself. Sorry, when you have a heat source inside, the internal core is this nuclear generating part. This is where the source of the luminous sky is basically from the energy that is powered by nuclear fusion. It's a fusion of basically hydrogen into deuterium, deuterium into helium, right? So you actually produce helium that settle into the core, by the way. So there's a small diffusion process. So there are some already certain amount of helium in it, in the inner core, that we shall never see until you can chop open the sun, of course. Then you get the outer region, which is a reaction to this hot ball and dense region, slightly more rarefied. Gravity is still important. And you have this region that is, the mode of the energy transport is by radiative transfer. So it's called radiative zone. Okay. And it turns out that this ball is so solidly rotating, it's very, very hard to make sure that, see that it's differentially rotating. So it's equal from pole to equator on this region. That's information we have from helioseismology, basically sound wave propagating. And outer region is really the reactive region. It's called the convective zone, where the energy is transported by fluid, actual flow, plasma flow, right? Basically hot stuff have to warm up and then cool stuff sink. That's the idea, right? Essentially you form, and then we're a narrow region. And then not only that, the reason why magnetic fields got generated is because the sun on the outer surface is differentially rotating. On the equator is about 27 days, on the pole is 40 days. This slow stuff, if you imagine you have a seed magnetic field, it wind up, right? It's wind up, right? And then through turbulence of the atmosphere, you have this what you call helical flow. They're called alpha effect. That you actually, these are very small scale, by the way. Stuff that we're talking about is basically the whole hemisphere of the sun. The heliosphere, I don't think we ever resolved them. It's on the much, much smaller scale that you can resolve really, because we never detected the heliosphere really. It's all in conceptual state. That is called alpha omega model. One is the alpha is the helical, omega is actually the differential rotation. These two effects, whether it's operating on the surface or near the bottom, the transition region between the radiative zone and the convective zone is called tachocline, by the way. There's a technical name for that. That's why the different, solid rotation inside. Twisting if there's a magnetic field, it twists it up, wind it up. And then allow the expulsion of this magnetic flux, because when you build up, the flux there is of the order of kilogauss. On the surface is only on the order of gauss, and then in the concentrated region where the sunspot appears, that's also kilogauss. Sorry, 100,000 kilogauss in the tachocline, those field. So they have to buoyantly go up, right? So that's basically the phenomenon of sunspot. And if you plot those phenomena of sunspot over time, it look like a magnetic wave actually. A wave. That's why it is described as a wave. It look like a butterfly wing that very broad from 45 degrees and then move towards the equator. This is where they're describing the sunspot cycle. But we found out already in 1908. George Ellery Hill at Mount Wilson Observatory. The time in which that we haven't got the Zeeman effect figured out, which is to detect on quantum mechanics sense that you have a spectral line. If the magnetic field is present, you split the line above and beyond what is being perturbed by pressure and all these other forces, but magnetic forces does that. So Peter Zeeman from Holland figured that out experimentally. And quantum mechanics, you can easily after that realize and show these effects to be real magnetic presence of this. And 1908, George Ellery Hill and Mount Wilson they started taking picture and then put a slit of this spectrograph and show some particular line that is sensitive. Actually is iron, one of the iron line that shows that it's actually in the visible wavelength, because that's when we can do at that time. It's about 6,000 angstrom, And 6,000, by the way, is a visible part about that, but it's slightly green. And they were able to show that they can find Zeeman effects. And the amount of split depends on the strength of the magnetic field. So early on, we already realized all this magnetic region, the dark spot region, in Latin is called maculae, M-A-C-U-L-A-E, right? And then the bright part is called faculae. It's like torch. Black one, I don't know what it means, but it means black spot probably, something dark. And that we figured out that it's strongly magnetic field region. Not only that, he figured out that magnetic field, you have to have polarity, right? Which means you have direction. So you figure out that this sunspot is actually one time is positively region, positive, and then the other side is going in, the other side is going out. So it's actually a 22 years magnetic wave cycle. That's basic understanding. The best bet After studying for many, many years, once the equation was found, essentially created by a guy like Eugene Parker, for example, to make the postulate that we can actually concisely define this system. The whole idea in search of mathematical science and physical sciences is try to understand this phenomenon, right? We have great observation to lead us, like Halileo Hill and then Monders and a bunch of those people. The Edward Monders and Annie Monders are this very famous observer of the sun. I call them solar observer. Very dedicated. They actually took the first photograph of the sun right around 1876 or so, until the year that he retired, 1928, and the year he died also around that time. He took that photo, and then it's been taken on by US Air Force till 1976. Now the program died, and then there's another group in Kitt Peak and Sack Peak that continue the program. But those programs essentially by now, 2018, is died because they want to focus money on big program, which is really not a very good direction in my view. Too sexy, and it's just not going to be big gain for the money. Always about fighting resources. So, the sun.